We'll start in 1 minute. We'll continue today in section 8.3 on rational exponents. So a repeat of a couple of definitions that we've already seen. If n is a positive integer, then the nth root of a is equal to a to the 1 over n. So this is an equation that equates a radical form to a rational exponent form. More generally, if m and n are positive integers, then the nth root of a to the m is equal to a to the m raised to the 1 over n. Using a property of exponents, you can multiply 1 over n times m and write it as a to the m over n. Or you can write it as a to the 1 over n to the m. So this form right here, a to the 1 over n to the m, is a nice form when simplifying expressions like we will see in a minute. Okay, but you can also write the nth root of a to the power n. So all 5 of those are equivalent. All right, we'll practice simplifying expressions with rational exponent. This one, 27 to the 4/3. So for convenience, we can write it as 27 to the 1/3 to the 4th. 27 to the 1/3, that's the 3rd root of 27. And the 3rd root of 27 is 3. So this becomes 3 to the 4th. And then 3 to the 4th is 81. 3 to the 4th is 3 times 3 times 3 times 3, which is 81. Okay, following the same procedure, 216 to the 2/3. We can think of this as 216 to the 1/3, and then raise that to the 2nd power. 216 to the 1/3, that's the cubed root of 216, which is 6. And so this becomes 6 to the second. 6 to the second is 6 times 6, which is 36. Okay, the next one, negative 25 to the 3 halves. So this one, note that the exponent 3 halves applies to positive 25, and then afterwards we take the negative of that. So another way to say this is that it's the negative of 25 to the 3 halves. It means the same thing as negative 1 times 25 to the 3 halves. And then if you remember the order of operations, we evaluate exponents before we multiply. Okay, but the 25 to the 3 halves, we can think of that as 25 to the 1/2 to the 3rd. 25 to the 1/2 is the square root of 25, which is 5. So this is negative 1 times 5 to the 3rd. 5 to the 3rd is 125. And then when we multiply that by negative 1, we get negative 125. All right, the next one, a little more complicated. This time we have 64x to the 5/7 raised to the 1/6. Think of 64 as 64 to the 1st power. And so we can distribute this outer exponent, multiply the outer exponent by each of the exponents on the inside. And we have 64 to the 1/6 times x to the 5/7 times 1/6. And then 64 to the 1/6, the 6th root of 64 is 2. And so we have 2 times x to the 5/42. So just a note, a related fact is that the number 2 raised to the power 6 is 64. So that's why 64 to the 1/6 is equal to 2. See what I mean? So a little more detail. Raise both sides to the 1/6. Two to the 6th to the 1/6 is 2 to the 6 times 1/6, or 2 to the 1st. So 2 is equal to 64 to the 1/6. That's the whole point there. Hey, the next example. Okay, this time we have in parentheses 4 times x to the 2/5 times y to the 3/5 raised to the 5/2 power. So we're just multiplying 3 terms on the inside of the parentheses. And think of 4 as 4 to the 1st, and then we're going to apply a property of exponents. We'll multiply 5/2 times each of the 3 exponents. And we'll get, in the first step, 4 to the 5/2 times x to the 2/5 times 5/2 times y to the 3/5 times 5 halves. Okay, in the next step, 4 to the 5 halves. We'll rewrite that as 4 to the 1/2 to the 5th. And then x to the 2/5 times 5 halves, multiply the exponents, we get x to the 10 over 10. 10 over 10 is 1, so we just get x to the first, or x. And then y to the 3/5 times 5 halves, multiply 3/5 times 5, 3/5 times 5 halves, we get the exponent y to the 3 halves. Okay, a couple of more steps. 4 to the 1/2, the square root of 4 is 2, so we get 2 to the 5th times x times y to the 3 halves. And finally, 2 to the 5th is 32. 2 times 2 times 2 times 2 times 2 is 32. So 32x times y to the 3 halves. Okay, the next one, we have y to, in the numerator, we have y to the 5/3 times y to the negative 1/3, and then we're dividing by y to the negative 2/3. So there's different things that we can do, but in the numerator, we can just start by combining y to the 5/3 times y to the 1/3. We add the exponents when we're multiplying two terms that have the same base. So we have y to the 5/3 plus negative 1/3. And then we're dividing by y to the negative 2/3. So let's simplify the exponent in the numerator first. So y to the 5/3 plus negative 1/3, we get y to the 4/3. And then divided by y to the negative 2/3. And we still have a couple of options. Remember, if you have something with a negative exponent in the denominator, you can move the term to the numerator and write the exponent as a positive instead of a negative. So if we do that, we already have y to the 4/3 in the numerator, and y to the negative 2/3 in the denominator is equivalent to y to the positive 2/3 in the numerator. So the denominator is now just 1. And then finally, y to the 4/3 times y to the 2/3. Since the bases are the same, the base is y, we can add the exponents. So y to the 4/3 plus 2/3, which is y to the 6/3. And 6 over 3 is 2, so our final result is just y to the 2nd. Okay, let's move on to the next page. So as usual, always read the directions. Okay, so this one, for these problems, convert the expressions to radicals and simplify if possible. Okay, x to the 3 halves. The denominator of the exponent is a 2, so the index of the radical is 2, which is a square root. When the index is 2, you don't need to write it, but we'll go ahead and write it. And then on the inside, we have x to the 3rd. This can be simplified. The square root of x to the 3rd. So to simplify the square root of x to the 3rd, we identified the largest factor of x to the 3rd that is a perfect square. So the largest factor of x to the 3rd that is a perfect square is x to the 2nd. Remember, with terms with variables and exponents, a perfect square is a variable raised to an even exponent. So x to the 2nd, x to the 4th, x to the 6th, x to the 8th, and so on. If the exponent is a multiple of 2, or if it's an even integer, it's considered a perfect square. So x squared is a factor of x to the 3rd because x squared times x is x to the 3rd. So we can rewrite this as the square root of x to the 2nd times x. Remember, with a square root, I don't need to write the index 2 if I don't want to. And then the square root of x squared times x is the square root of x squared times the square root of x. And finally, the square root of x squared is x, which we multiply by the square root of x. So this is our simplified answer. Okay, the next one, the term 5x raised to the 2/3. So since 5x is inside parentheses, the exponent 2/3 applies to the factor 5 and the factor x. So we want to convert it to a radical. The denominator of the exponent is 3, so the index of the radical is 3. And we want to make sure that we're careful about how we, or what we put on the inside of the radical. So what do we put on the inside of the radical?
Five to the second, x to the second. 5 to the second, x to the second.
Yes, 5 to the 2nd times x to the 2nd. And then 5 to the 2nd can be simplified to 25. So I'll do this in a couple of steps. So we can start by writing 5x in parentheses to the 2nd. If you write 5x to the 2nd without parentheses, then that's not correct. So this is a satisfactory answer, but we can take it further. If we square the term 5x times 5x, we get 25x squared inside the cubed root, the radical with index 3. All right, the next example, x to the 7/4, convert this to a radical. Okay, converted to a radical. The denominator of the exponent is 4, so the index of the radical is 4. And then we have x to the 7th inside the radical. And this can be simplified. The largest factor of x to the 7th that is a perfect 4th power is x to the 4th. So we can rewrite the 4th root of x to the 7th as the 4th root of x to the 4th times x to the 3rd, because x to the 4th times x to the 3rd is x to the 4 plus 3, or x to the 7th. And then the 4th root of x to the 4th times the 4th root of x to the 3rd. And then the 4th root of x to the 4th is just x. So our simplified radical is x times the 4th root of x to the 3rd. Okay, the next one, 8x to the 5/3. Convert this to a radical. The denominator of the exponent is 3. So the index of the radical is 3. And then we have the term 8x to the 5th. So on this one, let's just leave 8x in parentheses to the 5th. And the largest factor of 8x to the 5th that is a perfect cube is 8x to the 3rd. So let's rewrite this as the cubed root of the term 8x to the 3rd times the term 8x to the 2nd. And then the cubed root of the term 8x to the 3rd is just 8x, which we multiply by the cubed root of the term 8x in parentheses to the 2nd. This is a satisfactory answer, but on the inside of the radical, since we're squaring the term 8x, we can go ahead and square it. So we get 8x times the cubed root of 64x squared. Okay, the next example, y to the 2/5. Convert this to a radical. The denominator of the exponent is 5, so that means the index of the radical is 5. And y to the 2nd is inside the radical. And this cannot be simplified any further because the largest factor of y to the 2nd that's a perfect 5th power is just 1. So this is as simplified as it can be. Okay, the next one, the term 7x to the 8th in parentheses raised to the 3/4. So convert this to a radical. The denominator of the exponent is 4, so the index of the radical is 4. And then we have, in parentheses, 7x to the 8th to the 3rd. So this time, we'll apply, inside the radical, we'll apply the outer exponent 3 to 7 to the 1st times x to the 8th. And we'll get 7 to the 3rd times x to the 24th. Because 3 times 8 is 24. Well, 7 to the 3rd is just 343. 7 times 7 times 7 is 343. And the largest factor of 343 that is a perfect 4th power is 1. But the largest factor of x to the 24th that is a perfect 4th power is x to the 24th, because the exponent is a multiple of 4. So when we simplify this, I'll write the 4th root of x to the 24th multiplied by the 4th root of 343, because 7 to the 3rd is 343. And then the 4th root of x to the 24th, that is equal to x to the 24 divided by the index 4. 24 divided by 4 is 6. So we get x to the 6th times the 4th root of 343. Okay, in the next part, we'll do the reverse process. We'll convert radical expressions to rational exponents, or to expressions with rational exponents. The 7th root of x to the 5th. Well, inside the radical, we have x to the 5th. And a 7th root of something means to raise that something to the 1/7 power. And then we just apply a property of exponents. Multiply 1/7 times 5, we get x to the 5/7. All right, the next one, we have 3 times the 4th root of 2x. So this is 3 times the term 2x to the 1/4. So we need parentheses around 2x. So this is an okay answer if you want to leave it like this. But we could also write it as 3 times 2 to the 1/4 times x to the 1/4. Okay, in part C, the 5th root of 13x to the 4th. So inside the radical, we have 13x to the 4th. And then this is raised to the exponent 1/5. The denominator of the exponent 5 is the same as the index of the radical. And then take it one step further, 13 to the 1st times x to the fourth all raised to the 1/5. We can write this as 13 to the 1/5 times x to the 4/5. Okay, so this is probably seems like tedious work, but this is how you get good at knowing what the properties of radicals and rational exponents. This one, 2 times the third root, or the cube root of 5x to the second. So this is 2 times, and then in parentheses, 5x to the second raised to the exponent 1/3. And then this is, when we apply the outer exponent, we can write 2 times 5 to the 1/3 times x to the 2/3. Okay, in part E, 5 times the 11th root of y to the 9th. So this is 5 times y to the 9th to the 1/11. And then we get 5 times y to the 9/11. When we multiply 1/11 times 9, we get 9/11. Okay, the next one, the 6th root of 10y. So inside the radical, we have 10y. So 10 times y in parentheses with the exponent 1/6. So this is a fine answer, but we can take it one step further and write it as 10 to the 1/6 times y to the 1/6. All right, let's move on to the next page. Hey, we've seen problems like these before. This is just more practice. Simplify 64 to the 5/2. 64 raised to the exponent 5/2. So when simplifying expressions with rational exponents like this, then my suggestion is rewrite a to the m/n as a to the 1/n to the m. Then determine what a to the 1/n is, and then after you've found that, raise that to the power n. Okay, so that's what we'll do here. 64 to the 5/2. Think of that as 64 to the 1/2 to the 5th. 64 to the 1/2, that's just the square root of 64, which is 8. So we get 8 to the 5th. So you can use a calculator to determine what 8 to the 5th is. Or another way to do it, 8 is 2 to the 3rd, I mean. So you can think of this as 2 to the 3rd to the 5th. which is 2 to the 15th. So let's see. Well, 2 to the 15th. Or it might be easier just to find 8 to the 5th. I'll leave the rest of that for you to do. Okay, the next one, we have the number negative 64 in parentheses to the 2/3. So rewrite this as the number negative 64 in parentheses to the 1/3. And then we'll put in another set of parentheses and an outer exponent of 2. Okay, the cubed root of negative 64, what's that?
-4.
Yeah, -4. The cubed root of negative 64 is -4. In general, the cubed root of a negative number is a negative number. So we replace the cubed root of negative 64 with -4 in parentheses to the second. And then the number -4 in parentheses to the second is positive 16. Okay, the next one, 100 to the 3/2. Rewrite this as 100 to the 1/2 to the 3rd. 100 to the 1/2 is the square root of 100, which is 10. So we get 10 to the 3rd. 10 to the 3rd, 10 times 10 times 10 is 1,000. Hey, we have some other properties to practice next. B to the 1/4 times B to the 5/8. We are multiplying two terms that have the same base, b, so we can write the base b and add the exponents. So b to the 1/4 plus 5/8. And then simplify 1/4 plus 5/8. The common denominator is 8, so rewrite it as b to the 2/8 plus 5/8. And then finally, b to the 7/8. The next one, 6 to the 5/2 times 6 to the 1/2. So the same properties that were in the previous one will apply here. We can write this as 6 to the 5/2 plus 1/2. 5/2 plus 1/2 is 6/2. 6/2 is 3, so we get 6 to the 3rd. And 6 to the 3rd is pretty simple to evaluate. 6 times 6 times 6 is 216. All right, the next one, y to the 1/2 times y to the 3/4. So we're multiplying two terms that have the same base. So we write the base and add the exponents, 1/2 plus 3/4. And then 1/2 plus 3/4 is equivalent to 2/4 plus 3/4. And finally, y to the 5/4. Okay, in the next row, we have a different property of exponents to apply on this one, but we've applied it a few times already. K to the 12th raised to the 3/4. So this time we're going to multiply the exponents, and we get K to the, you can think of 12 as 12 over 1 multiplied by 3/4. And then you can simplify the exponent in a couple of different ways. One way is just to multiply the fractions, 12 over 1 times 3 over 4 to get 36 over 4. And then 36 over 4 simplifies to 9, so we get K to the 9th for our simplified result. All right, the next one is the same property. A to the 15th raised to the 3/5. We multiply the exponents, so A to the 15 over 1 times 3/5. Another way, instead of just multiplying the fractions, you can look for common factors that cancel. 5 goes into 5 once and into 15 3 times. So we get A to the 3 over 1 times 3 over 1, or A to the 9th. The next one, X to the 10th, is raised to the 5/2. So we multiply the exponents again, X to the 10 over 1 times 5 over 2, which is X to the 50 divided by 2, or X to the 25th. Okay, in the next row, inside parentheses, we have 16 times m to the 1/3, and that is raised to the 3/4 power. So 16 is the same as 16 to the 1st, so we're going to, when we apply the outer exponent, we're going to get 16 to the 3/4 times m to the 1/3 times 3/4. 16 to the 3/4, rewrite that as 16 to the 1/4 to the 3rd, and then times m to the 1/4, because 1/3 times 3/4 is 3/12, which simplifies to 1/4. And then we still have to simplify 16 to the 1/4 to the 3rd. 16 to the 1/4 is 2, so we get 2 to the 3rd times m to the 1/4. And then finally, we get 8 times m to the 1/4. All right, the next one, a little more going on here. 9 times x to the 2/5 times y to the 3/5 is all raised to the 5/2. So remember the exponent of 1 on the factor 9. So when we apply the outer exponent, we get 9 to the 5/2 times x to the 2/5 times 5/2 times y to the 3/5 times 5/2. Then 9 to the 5/2 we'll write that as 9 to the 1/2 to the 5th. And then times x to the 2/5 times 5/2 is x to the 10 over 10. And then y to the 3/5 times 5/2 is y to the 15 over 10. 9 to the 1/2 is 3, so we get 3 to the 5th times x to the 1st times y to the 3/2. And then finally, 3 to the 5th is 243. So 243 times x times y to the 3/2. Okay, the next one, a to the 3/5 times a to the negative 1/5 in the numerator, and we're dividing by a to the negative 11/5. So we can begin by simplifying the numerator. We add the exponents, so we get a to the 3/5 plus negative 1/5. And then we're dividing by a to the negative 11/5. A in the numerator, a to the 3/5 plus negative 1/5 is a to the 2/5. And in the denominator, right now we still have a to the negative 11/5. And remember, a to the negative 11/5 in the denominator is equivalent to a to the positive 11/5 in the numerator. And now the denominator is 1. And now in the numerator, a to the 2/5 times a to the 11/5 is a to the 2/5 plus 11/5, which is 13/5. Okay, the next one is similar to the one we just did. We can begin by simplifying the numerator, n to the 7/8 plus negative 5/8 divided by n to the negative 3/8. And in the numerator, we get n to the 7/8 plus negative 5/8 is n to the 2/8 divided by n to the negative 3/8. It is true that 2/8 simplifies to 1/4, but you can anticipate that we're going to need the 2/8 in the next step anyway. So when we simplify n to the 2/8 divided by n to the negative 3/8, we remember that n to the negative 3/8 in the denominator is equivalent to n to the positive 3/8 in the numerator. The denominator is now 1. And then we get n to the 2/8 plus 3/8, which is n to the 5/8. Since the denominator is 1, we don't need to write over 1. So n to the 5/8. Okay, there's still a minute left. I can probably find a problem from a couple of days ago that we didn't finish. Maybe. That one. Yeah, this is from Tuesday. So these should seem easy by now, maybe. Simplify the cubed root of y to the 26th. So what's the largest factor of y to the 26th that is a perfect third power or a perfect cube? So if you have variables with exponents, what are the perfect cubes? I'll use the variable y. So y to the third is a perfect cube. Y to the 6th is a perfect cube. Y to the 9th, y to the 12th. If the exponent is a multiple of 3, it's considered a perfect cube.
Y to the 24th.
Yeah, so y to the 24th is the largest factor of y to the 26th that is a perfect cube. And y to the 24th times y to the 2nd equals y to the 26th. So then we can write the cubed root of y to the 24th times the cubed root of y to the 2nd. And then the cubed root of y to the 24th is y to the 24 divided by 3, or y to the 8th. And then so y to the 8th times the cubed root of y to the 2nd is the simplified answer. All right, we're over time now, so go ahead and sign in for attendance. Yep.